Ladies and gentlemen, today's class recording has started. So, on Friday, we began talking about Newton's first law and Newton's second law, two important concepts dealing with force. But, backing up just a little bit, let's review about force, right? First, force answers a question for us, very similar to the questions we were talking about in the previous unit. When we describe motion, we want to know where something is, what it's doing, what it's going to do next, and when are all those things happening. What question did we say that force answers for us? So when we talk about mechanics, we talk about where, that's displacement. We talk about what, that's velocity. We talk about what next, that's acceleration. And we talk about when, that's time. But we said force answers another important question for us. What is that other important question that force answers for us? How or why, right? How or why do all these things happen? And so, that being said, we talk about Newton's first law and Newton's second law. So, Newton's first law describes what for us? Frank? So object at rest remains at rest. Object in motion continues in motion until it experiences a net force. To summarize that up, we use one word. What is that word? Inertia, right? So inertia basically is an object doing what? Or an object not doing what? Inertia describes an object that is not changing or accelerating, right? Newton's first law deals with things staying the same, right? Doing whatever they are currently doing. If they are sitting still, great. They will stay sitting still. But if they're moving, they want to continue moving, right? Good with that. Okay? And we call that idea inertia, right? The tendency for an object to resist changes in motion. Resist changes in motion, not accelerating. Okay? Good there? And so, a couple of things that go along with that. First, we talked about mass. And we said mass tells us about how much inertia something has, right? The more mass it has, the harder it is to change what it's doing. That could mean getting it to start moving, but also could mean getting it to stop moving, right? But then, an important concept that we talked about was net force. When we describe the net force, what are we talking about? Without just reading it to me off the board. Eric? The total force, or looking at all of the forces that are acting on something, not just one individual force, but all of the forces, and figuring out what is that combined effect. Right? We use the notation sigma to represent net. Sigma represents net, and mathematically when we see sigma in front of something, what does that tell us to do? The sum. Add them all up, right? Find out what the total is. But something we have to keep in mind, right, is that forces are vectors. So if we have vectors pointing in opposite directions, we may be adding them, but sometimes mathematically that means we're adding what? A negative number, and then that's kind of like subtraction. All right, good with those concepts. Okay, let's take a look at the first page of the packet I gave you. You may see that I couldn't find the actual copy of this worksheet. I could only find the answer key. So answering the questions on this first page isn't so difficult because they're basically already circled for you. All right, so let's talk about those questions, and let's start here. All right? So it says, an astronaut in outer space, away from gravitational or frictional forces, throws a rock. That rock will. And the correct answer is continue moving in a straight line at a constant speed, instead of gradually coming to a stop, right? We talked about here, everything that is moving eventually stops. Why do things here eventually stop, right? Friction, right? And friction is a what? A type of force, and that means it causes things to do what? Accelerate. Specifically, what type of acceleration, Frank? Slowing down or negative acceleration, right? Generally speaking. Not always, but generally speaking for friction. Okay? But if we take it away, right? Away from gravitational or frictional forces, the astronaut gives that rock an initial push and causes it to positively accelerate, to speed up. But once that rock leaves the astronaut's hand, are there any forces acting on it? If there's no gravitational or frictional forces, then no. And that means what will the rock do? Remain in a constant, not constant acceleration, constant velocity, right? Constant velocity means two things, yes? For something to have constant velocity, what has to be true? Same speed, same direction. So this rock is just going to keep going and going and going and going and going. Until what? Until a force acts on it, right? Or we should probably say, if we want to be a little bit more accurate than that, not just a force, but a... We talked about one term, right? A net force, right? So if, for some weird coincidence, at this very moment in time, and don't ask me how this would happen, let's just say it could, right? If a force started pushing down on the rock like this, and then another force started pushing up on the rock like this, don't ask me how that would happen, but let's just say it did, all right? Would anything change about that rock's motion? No. It's experiencing forces, right? But what do those forces do to each other? Basically cancel each other out. So even though there were no forces before, but now there are two forces, the net force is still what? 0. Okay? Good there? And this idea, right, we call inertia. Okay? So, did I show you guys the ball and the string on Friday, or was that the other class? Yeah. Ball and a string. Okay? Alright, so ball and a string. Ball and a string. Okay? First, is this ball accelerating? Yeah. Yep, change your direction. Good job. So, this ball is constantly accelerating. And if it's constantly accelerating, what does that mean it has to have? A net force, right? An unbalanced net force. Okay? What's providing the net force to the ball? Technically, no. Am I touching the ball? No. The string, right? The string is providing the net force, right? And it's causing this ball to continuously accelerate. Okay? If I was to let go of the string, okay, if I was to let go of the string, I won't do it here, I'll actually move to another place to do it. If I was to let go of the string, what's going to happen? The ball is going to, okay, move. How is the ball going to move? It's going to continue in its path. What kind of a path up? If it's going to continue in its path, will it continue to go around in this circle? No. Right? Is this circle a natural situation? Things don't like circles, right? Because circles aren't constant velocity, right? This is constantly changing velocity. It's not speeding up or slowing down, but it keeps going in a different direction. So if I don't make it go in a different direction, what is it going to do on its own? How is it going to travel on its own? Well, if I don't make it go in a circle, how is it going to travel? In the same direction, right? So to answer this question right up on the board, okay, this is looking at it from the top, okay? Right? If that string breaks at the very, very top of the motion, the path that the ball follows is C. Why? Because it's what? 2 up on the board, right? Which is also number 2 on the sheet that I gave you. Okay? If the string were to break at the very, where the ball is very, very at the top of its motion, right? It won't keep going in a circle like D. It goes like C. Why? Well, what's C compared to the other 3? A straight line, right? Technically, A is a straight line too, but it's not going that way, right? Okay. Do things go in circles on their own? Things go in straight lines on their own, right? Does that make sense? Okay. So here. Okay. So if I let it go and it's at the top of the motion, where's it going to hit the wall? Is it going to hit the ball above the door?
Yes.
Right? When it's at the top of the motion, it's going this way. And if I let go of the rope at that point in time, is there anything to make it change direction? Straight line. Good? Does that make sense? Split between the head.
Break the wall.
That's what I'm looking for. This wall's already broken. Right next to Amanda, there's a spot in the wall that, like 3 years ago, somebody like ran their desk or their chair into it, and that just like came off. Like, great, new building. So I'm gonna teach you. Ready? Here we go. Straight line. Okay. Good there. Okay. Let's look at a different situation. Okay. Here's a guy holding a pencil on a bus. And I'm going to use this baseball to illustrate the same idea. Okay? So, take this baseball and I throw it up in the air. It goes up and it comes right back down to my hand. Right? Okay. Was it accelerating?
Yeah.
Yeah. Because of what?
Gravity.
Gravity, right? Gravity slows it down on the way up, speeds it up on the way down. We talked about it like 15 times last chapter, yes? Okay. Velocity decreases, velocity is 0 at the top. Is the acceleration 0 at the top?
Yeah. No.
Nope, right? Even though it stopped, it's going to start moving again right away, right? So slow down, change directions, speed back up, okay? So I can do that as I'm here, right? But I can also do it if I do this. Alright? So, if we're watching the recording, obviously that doesn't make much sense, but I'm walking across the front of the room, throwing the ball up and catching it in my hand. Is the ball going up and coming back down? Yes, but it's also doing what? Which way? Moving forward as well, right? But each time it comes right back to my hand. Why? Because I'm moving forward too, right? When I push the ball upward, it's already moving forward. So what is inertia telling it to do? Go forward, which is fine. But now there's a force acting on it, right? First the force from my hand pushing it upward. Then the force of gravity pulling it downward. But those forces are acting up and down. How are they not acting? Side to side, forwards or backwards. So if this ball is already moving forward, it'll keep moving forward until there's a net force on it. But that net force has to be, does a net force up and down change what's happening side to side? No. So the whole time that this ball is in the air, slowing down, speeding up, it's also continuing to move forward, right? So I can hold this ball in my hand, go up and down, and it comes right back in my hand. I can walk forward and do exactly the same thing, because that forwards motion continues on and there's nothing to stop it. So it doesn't stop. It just keeps going. Right? This same thing would work if I was sitting or standing on a bus, going forward way faster than I can walk in this classroom. Does that make sense? Right? This exact same thing would work if I was on an airplane, going 500 miles per hour. Because there's nothing to stop that forward motion. Does that make sense? An example of inertia, right? If I start the ball moving forward, it wants to continue moving forward until something makes it stop. And if there's nothing to make it stop, it won't. Right? So, suppose you're standing on the aisle of a bus, traveling along a straight road at 100 kilometers per hour, which is about 60 miles per hour. You hold the pencil still above your head. Then, relative to the bus, the velocity of the pencil is 0. Is the pencil moving? Yes. But what else is moving? The bus and you. So it looks like it's standing still, but really everybody's moving the same way. Good? At that moment, the pencil has a horizontal velocity of 100 kilometers per hour with the bus. Right? But now you drop the pencil, or drop this baseball, or whatever it is that you might be holding. Right? While dropping, the pencil still has a horizontal velocity of 100. After you let the pencil go, is there a net force acting on it? Yes. Jack's right. Somebody else tell me what the net force is acting on the pencil. Gravity. But gravity acts which way? Downward. Does it affect the forwards motion of the pencil? Doesn't, right? So, well, it says while dropping, the pencil still has a horizontal velocity of 100, right? And that means as it falls, it continues moving forward. But if you're on the bus, you continue moving forward as well. So this pencil will land right by your feet, just like it does if you drop it here in the classroom and I'm not moving. Does that make sense? All right? Relative to you, the way the pencil dropped is the same as if the bus were at rest. And that's true as long as what? As long as what doesn't happen. Or
change direction.
Okay? This experiment works perfectly fine as long as I don't accelerate and as long as the ball doesn't accelerate. Right? If I do this, ready? Okay? It didn't land in my hand. How come? I stopped. What did the ball do? Kept going, right? This is going to take some coordination. All right, ready? Ball didn't land in my hand. Why not? Ball accelerated, right? But as long as nobody accelerates, as long as me and the ball keep going, nothing happens. Same thing lands right in my hand. Good there? Good. Okay. At the bottom, there's a blank space. It's not filled in for you. It says, how does this example illustrate the law of inertia? Talk to the person next to you and come up with a way to explain how inertia is responsible for this behavior. Discuss. Go. this is how the book described it. You don't have to copy it this way, but your answer should have something that sort of looks like this, right? Body in motion tends to remain in motion as long as no net force is exerted on the body in the direction of the motion, right? As that pencil is dropping through the bus or as the ball is flying through the air, it has a net force on it. That net force is gravity. But gravity affects things up and down. It doesn't affect things side to side. So that horizontal motion just keeps going as long as there's nothing to stop it.
I think it looks like when you throw the ball, it looks like it just stays in the exact same place like that. There's no way to move at all.
When I'm doing what?
Like when you were walking from the ball, it looks like it didn't move at all.
Ah. Are you ready?
Yeah.
Okay. I'm going to throw the ball right when I get to the edge of the desk. Okay. Ready? Does that make sense?
So I guess it's just because you're in the same place when you touch it.
Yes. There's a word here or a phrase that could help us understand it. It's one of the first physics terms we discussed. Anybody want to help him? I know it's a very vague question. It's your frame of reference, right? Why doesn't it look like the ball is moving forward? Because you're moving forward with it, right? So, but now here, because you're watching me, your frame of reference is kind of my frame of reference, right? But if we take a step back and use something that isn't moving as the frame of reference, now we can see that horizontal motion is occurring. Does that make sense? Okay. All right, good there. Good with this? You guys have something written down that sort of kind of looks like this? Okay. So Newton's first law deals with inertia. Newton's second law deals with what? Summarize. What does Newton's second law tell us about? Newton's first law tells us about inertia, or things not accelerating. Newton's second law tells us about acceleration. And we learned on Friday that acceleration is affected by two things. What are the two things that determine the acceleration of an object? The net force and the mass, right? And we summarize the relationships between net force, mass, and acceleration with an equation. And that equation looks like this. Okay? We can also rearrange this equation to look like this. Okay? Good there? This equation tells us about how these three things are related. So, what kind of relationship exists between net force and acceleration? You can look on the back of your outline if you want to, or you can just look at this equation and figure it out. They are directly related, right? Here, acceleration is the answer to a division problem. Net force is on the top of that division problem. If we make the top of a fraction bigger, what happens to the answer of that fraction? It gets bigger as well, right? As long as we do what with the mass? As long as mass is constant, right? What kind of relationship do acceleration and mass have? Inverse, right? If mass goes up, it's in the bottom of the fraction. What happens to the answer of that fraction? It goes down. Okay? Good there? All right. Take a look at page 2, the back of that first page of the outline that, or the packet that I gave you. Okay? It tells you up at the top of the page, I didn't copy this part, cart A has a mass of 1 kilogram. So, here in number 1 it says cart A is pulled with a force of 1 Newton. Alright? So, for cart A, we know that the net force is 1 Newton, and it told us that the mass was 1 kilogram. So we have 1 over 1, so what's the acceleration of cart A going to be? 1. Alright? Well, Newton is actually a derived unit. Okay? And we said derived units are combinations of base units, right? Here is the combination of base units that makes up a Newton. Okay? Does that make sense? Well, are you okay with just that? That's the combination, right? So now, if we take this and plug it into here, we end up with 1 kilogram times meter over 1 second squared all over 1 kilogram. Does that make sense? Okay? So, what do you see in that whole conglomeration twice? 1 kilogram shows up twice, right? So, if we cancel this and cancel this, now the only units that are left are what? Meters over second squared, and we know that's the unit for what? Acceleration. Okay?
Good morning, everyone. Pardon the interruption for a quick announcement, if I could have your attention. I'm making this announcement prior to our first lunch because it seemed to make a lot of sense. This week, starting today, is the May Dugan Food Drive. We will be collecting non-perishable food items, canned food, all week, and storing it in the lobby of the PAC. Students, if you bring any food items in, we ask that you drop in the lobby of the PAC. It'll be obvious where they're to be stacked, or you can drop them in the main office, and we will transport them over. On Friday night at the football game, there will be collection tables at the gates, so please, you or encourage your friends or family to also bring a food donation for May Dugan to the gate. They will also accept a cash donation. Amherst Steele High School is also participating in this endeavor this week to contribute to the Cuyahoga County Food Bank at May Dugan. They are also going to have their fans and supporters bring food to our gate. So please get involved. As I said, I made that announcement before lunch. As we are filling our stomachs today, it's an important time to reflect on the fact that there are many, many people in Cuyahoga County who will go home this evening not sure where supper is coming from. That comes from places like May Dugan. So let's really make an effort to support it. Reflect on it today and get mobilized. I know that the Demons can have a great turnout. All right? Everybody have a great morning. We will talk to you later.
Everybody okay with this first example here? See where I got it from? All the numbers showed up? Yep. So, here, right? Same thing for card A. Okay? But now this time, card B has a mass of 2 kilograms pulled with a force of 1 kilogram. Or, sorry, 1 Newton. So what's the acceleration now of cart B? It's only 0.5 meters per second. Squared. Sorry. So, who has greater acceleration? Oh. Good there? Okay. Here, right, cart B had, in the first example, cart B had the same mass, but experienced more net force. So what happened to the acceleration? If net force went up, what happened to the acceleration for cart B compared to cart A? It went up, right? Does that make sense? But here, cart A and cart B, well, sorry, in this case, they are experiencing the same force, right? But how does the mass of cart B compare to the mass of cart A? It's bigger. So if mass is bigger, what happens to acceleration? It decreases. Does that make sense? For number 3, right? Cart A, still 1 Newton of force and 1 kilogram. But what does it tell you now about cart B? Well, how much force is cart B experiencing compared to cart A? Twice as much. But how much mass does it have? Twice as much, right? So if we plug those two numbers into the equation, right? 2 newtons, but experiencing 2 kilograms, what's the acceleration now?
1.
1. So which one has the greater acceleration?
Same for both.
Same for both. All right? All right. We'll pick this up tomorrow and gather some data for our lab, so make sure these packets come back to me tomorrow, all right?
So we don't have to do it for homework?
No, we'll go over some more tomorrow in class. Tomorrow, actually, I will assign you guys your next quiz. Take home, okay?